All right, welcome. This is the AP Physics workbook solution. Here we have Unit 3, Circular Motion and Gravitation. The section is 3.L, which is Inertia in Space. So here's the scenario. A donut space station is built far away from the gravitational field on Earth and other massive bodies. For the comfort and safety of the astronaut, the space station is rotating to create a artificial internal gravity, right? Because again, that gravity is the result of the rotating and the changing of velocity in a circle. So that means there's going to be a centripetal acceleration inwards. Okay. Um, so therefore, you're gonna feel right gravity in the opposite way. Okay. The rotational speed is such that apparently the acceleration due to Earth at the other surface is 9.8. Okay. All right. So the astronaut here is feeling 9.8. Okay, so on the right, you're going to sketch and label the vectors that represent the astronaut's velocity and acceleration. And at the that's part A. Okay, to get you a better understanding here, there's a scene from the movie The Martian that I'm going to show you that gives you a great visualization of this part. All right. Okay, let's see it. All right. Okay, I'm going to turn off the music so I don't get copyrighted. But watch. You see from his point of view, she's rotating, right? Okay. And you see, but from her, she's actually stationary, right? It looks like she's actually upside down, right? No, she's actually stationary. Look, from her point of view, he's rotating, right? So again, it depends on the reference frame. Do you see how the space station is revolving right there? That's what's causing her to feel the force. All right? So that should give you a better understanding of what's happening here. All right? So the astronaut, she was actually moving. Okay? So from her point of view, from the astronaut point of view from the outside looking at her, okay? Oh, this should be straight. She was traveling that this needs to be straight. Yep. That was the velocity. And the fact that the velocity is changing, okay, because it's going in a circle, there is going to be a result in acceleration. Why? I need this to go straight. Okay. Yep. Hey. Perfect. All right. So on the right here, draw represents the astronaut standing in the space station. Draw a free body diagram showing the label of the forces. So towards the center, she feels the that should be straight. Force normal, right? Because remember, the floor was on the. So technically, here, let me write this for you so you can see it. Technically, this was the ground. Remember? In the picture, this is the ground. Technically, right? That's the ground, the space station. So she was feeling the gravity, right? Force of gravity there. Did I do a horrible job? Yep. It has to be the same length, force of gravity. All right. Good. Okay. Let's see here. So the next part, the astronaut drops the ball, and following on the diagram, sketch the velocity and the acceleration of the ball as seen by an observer outside the space station. So again, that was the astronaut outside, remember, watching her revolve, but this time she threw a ball. Okay, I'm just going to give you the answers here, but and the next part, there's going to be the explanation, okay? All right, so let's just go down here, and she was going forward to the right, right, and boom. That was the velocity of the ball. Was going this way. Okay. And then part C, he drops the ball on the velocity. Sketch the velocity and acceleration of the ball as seen as the observer outside the space station. So from here, this is after the ball hits the floor. How would it look like? right? So would it be still like this? Nope. It wouldn't be like this, okay? Right? Because it turned. So, whoops. So the ball turned a little bit, okay? Well, not turn, but the reference frame looked like the ball turned because, again, it's revolving around the circle, and the acceleration was still pointing towards the center. So, here you go. There is still a centripetal acceleration pointing inwards. And what was traveling in that pathway was the ball. So that's velocity. So, from the point of view from the outside, which path does the ball looks like? We would say here. From a person outside the space station, the ball looks like it's just traveling straight to the left. Okay? The reason why it just travels looks straight to the left is because, again, it's revolving. Okay? Now, and here's the next part. What does the path of the ball look like? Again, it says straight, right? Okay, from the point of view of the astronaut inside the space station, what does the path of the ball look like? Well, okay. Well, from the inside of the space station, okay, right? This is the astronaut inside the space station. So, to the from um, the point of view of the astronaut inside the space station, the ball appears to what? Fall down due due to the force due to the force of gravity-ish, right? You can't really call it the force of gravity. It's really the pull or the force of their centripetal acceleration, all right? So it's being pulled, let's say it's from the point of view of the astronaut inside the station, what does the path of the ball look like? From the point of view, the ball appears to fall uh, straight down. Let me just say straight down. And you know what? Without getting complicated, I'm just gonna say it here. I'm not gonna give it a a reason why the ball goes down, but we should understand why. Okay, that's it. That's all the answers for this one. Okay, and again, if you would like a better explanation of this, watch the video. Okay, watch the video again, and it should give you a better understanding of point of view. All right. So there you go. Those are all your solutions.